Good evening. Thank you very much, Thomas, for these kind words, and thank you guys for braving the cold December to be here. What is the theory of everything? Well, hopefully I'm going to take a journey with you tonight over 4 centuries of a dance between fundamental physics, pure mathematics, and data science. So let's try to find out. Since the very dawn of civilization, humanity has gazed up to the night sky. And we saw the passage of great arcs of the stars. Except 5 points. They're called the planets, from planetes, the Greek, the wanderers. They wander. This is the trajectory of Mars. Mars doesn't go like this, like the rest of the stars. It goes in this, what we now call retrograde motion. And here are the retrograde motion in various ancient languages. Everybody thought about this. It's obvious. There are these 5 exceptional points to the naked eye. So that was a bit bizarre. Why should there be these exceptions? Well, we have to wait several centuries, in fact, millennia, because in the Ptolemaic world, the geocentric world of the universe, Earth was at the center, right? And we had to wait until 1543 for this gentleman, Nicolaus Copernicus, to put something else at the center. Here is the first diagram of the solar system in print in the 1543 book of Copernicus, De Revolutionibus Orbium Celestium, on the revolution of the orbits of the heavenly bodies. And incidentally, by the way, 2 very interesting facts. 1, this word is where we get the word revolution from. Like, oh, the French Revolution was pretty radical. Well, it came actually from this book in this modern usage, because he was thinking about the revolution of the planet. It was such a radical and revolutionary idea that this has seeped into our common culture. Fantastic. Second fact, note the date of publication. That is the same as the year of his death, because it was so controversial, he couldn't publish in his lifetime. Stories have it that Copernicus was cuddling the first print on his deathbed. I like to think of that image. It's a beautiful image. So we've now moved from the Ptolemaic system to the Copernican system. Suddenly, geocentrism became heliocentrism, where the sun is in the center. And all of a sudden, this retrograde motion of these planetes became apparent and more naturally explainable. In the parlance of modern data science, this is called the optimal latent representation of data. What Copernicus was doing was to find a better representation just by shifting the center of your geometry. That's why it's so revolutionary. Fast forward 30 years. Johannes Kepler. You may or may not remember this from school. This Kepler's 3 laws of planetary motion. I'm not going to get into the details, but Kepler had the exquisite data of Tycho Brahe, from which he extracted, actually, that diagram of the solar system is wrong. They were circles, but they're not circles. They're ellipses, elongated circles. And the 3 laws of Kepler, right, explained exactly what these ellipses are and how they move around these ellipses, 30 years after. In the parlance of modern data science, this is called a model refinement. Okay? It's kind of interesting. They certainly did not use these words. Right? But this is still unsatisfying. Can we do better than to model the universe? Can we explain the universe? Can we derive the universe? And that is an ancient question. Does there exist a unifying principle of reality? Does there exist a fundamental description of nature from which we can derive models? Here's a very different concept, right? There is modeling reality and nature, and then there is coming up with some description of a fundamental law from which you can extract all the laws of nature. Is that even possible? Well, something happened in 1687. I'm very biased. I like to think that human civilization splits itself beautifully into two eras, before 1687 and after 1687. So what happened in 1687? And Londoners here should be very, very proud, because it happened 3 blocks down, Burlington House, where the Royal Society used to be. And it was the publication of Philosophiae Naturalis Principia Mathematica, the mathematical principles of natural philosophy. And of course, you know well, of Sir Isaac Newton. Now, why do I emphasize this date so much and this book so much? It's because this book began something quite different from everything I've mentioned so far. It's not just modeling data. It gave something quite different. It gave an underpinning, a set of equations from which you can derive the motions of the planets and all that there is. I will show equations. I'm a mathematician, so I cannot resist. If you don't like equations, you can sleep for 3 seconds. Now, you may or may not have seen, I think that's not true. I think all of you here will have seen these equations in school. And the vast majority of us then try ferociously to forget them. Why? Because they were shoved down your throats. Here's the law of motion. Well, in that book I just showed, the Principia Mathematica, it laid out Newton's laws of motion, the Newton's laws of gravity. You beat yourself, you memorize them, done. But that's exactly what you should not do with equations. Equations are to be enjoyed, like art. We're going to get that in a minute. So the first equation is equation of motion, the second law of Newton. The second one is the universal law of gravitation. Now, every first year mathematical physics student, some of mine I think are here, will have gone through the derivation in about 2 pages to show that this is sufficient to derive the precise motion of the apple that supposedly fell on Newton's head and give the elliptical orbits of the planets of Kepler to magnificent precision. All of a sudden we have something different. That is the importance of these equations. We're able to not model nature. We can explain nature using the language of mathematics. Newton had to invent a branch of mathematics which we now call calculus in order to do that derivation. And it's a beautiful, I can do it, we can do this. It's only half a page, 2 pages. It gets more and more complicated as we go along 4 centuries. Right? But isn't that wonderful that we can do this, that this is even conceivably doable? See, this wasn't emphasized to you in school. So I'm doing the damage control here. So that was 1687. This is 2021, almost 4 centuries. By the way, a lot of it happened in this very building. So in 4 centuries, what have we gone through? Right? Newton started, that book started what we now call the branch of science, which I think is the noblest of all branches of science, called mathematical physics. But in principle, what it is what we call scientific reductionism. The fact that you can reduce things through the language of mathematics to a minimal set of equations. That is the key. So, I've only given 8 pictures here because, they look pretty. By the way, I just want to thank Roman. I've given many of these public talks, and my slides were absolute crap until I met Roman. So Roman's a web designer for the London Institute. He's made this beautiful, and that's a theme we're going to go back over and over again. So I've just named, so, there's Maxwell, Einstein, and Bohr, and Hawking, C.N.Yang, so on, so on, so on. So through 4th century, great, magnificent geniuses have followed this path of Newton to do what? To try to reduce to a minimal set of equations. Just to give you an idea, Maxwell unified in the sense of Newton, right? Newton put those two equations and unified together to explain two completely different things, motions of apples and trajectories of planets. Maxwell, what did he do? Well, he unified electricity and magnetism and light into a set of equations which we now call the Maxwell's equations. Albert Einstein, I think you all know, what did he do? Well, he unified light with space and time and electromagnetism in a theory which we now call relativity. And so on, and Bohr and Heisenberg, they unified things into this framework called quantum mechanics, and so on and so forth. 4 centuries of scientific reductionism. 2021, where we are. Where are we today? How are we doing on this? Well, it's quite remarkable, because we've gotten it down to 2. Like really, seriously, 2. And that's it. Everything in the observable universe can be derived from these 2 sets of equations. It's no longer 2 pages of calculus in a freshman tutorial. It's about 10,000 pages. But it's okay, but that's what we do for a living. We want to fill up, boards like this. Right? So let me just walk you through these equations. They're so beautiful. The left-hand side is what's called the standard model quantum field theory. This is an equation which describes the microcosmos, the tiny world of subelementary particles that interact, like photons, light, electrons, quarks, every constituent force and particle of the universe. That's on the left. On the right is the equation that describes the macrocosmic world, the world of the evolution of the universe, the history of the universe, the motions of stars and galaxies, centers of black holes and whatnot. Right? So the technical term, this is called the standard model Lagrangian. There's there. And the right is the Einstein-Hilbert action for general relativity. I just want to emphasize that these 2 sets of equations have been checked to agree with experiment and experimental data more than anything that has ever been done in the history of humanity. This should give you an idea. This standard model Lagrangian, I'm not going to bore you with explaining every single term, has been checked up to 19 decimal places of precision. In other words, you calculate your Feynman diagrams, you do your calculation, after 20,000 pages, you get a number, you check with that in experiment from CERN, they agree to 19 decimal places. To give you an idea how good that is about the size of the solar system to within the width of 1 human hair. That's how precise experiment agrees with theory. Right? Nothing has ever been checked to this. We want to check this because this is the fundamental theory of everything. Here's a cute fact. That little phi here, that's the Higgs boson. That's what got the Nobel Prize for Peter Higgs in 2014. They discovered in this 2014, Higgs predicted in the 1960s. You had to wait many decades for this experiment. Now, I'm going to get back to this over and over again. So that's so cute, right? This is the God particle. This term gives mass to everything. That's why it's the God particle. And it's been checked incredibly, right? Move on this side. This is the 2018 discovery of the gravitational wave. The gravitational wave is the graviton g mu nu. The little g mu nu is part of the Einstein tensor. Little g, not big G. Okay, catch me on the street one day, I'll tell you the difference between big G and little g. That little one has been measured to a p-value of that. I'm not an experimentalist, but I can look at this numbers like, wow, that's pretty darn good. Right? Whatever it is, it looks amazing. So that got the 2018 Nobel Prize in the LIGO experiment for the detection of gravitational waves. So bottom line, both equations are checked to agree with experiment, just like Newton's classical law of motion agreed with the classical planets to incredible precision back in their day. Of course, that was revised by Einstein in the precession of Mercury, and then also agreed to incredible precision. So that's really great, right? That we got these two sets of equations from which we can derive everything, and they agree. How cool is that? Only in 4 centuries. In 4 centuries, our species is capable of doing that, right? That's not bad. Well, of course, okay, I've got to give, I'm a fanatic, right? I put this 1687 pretty dead on, right? But it's not really, it's much more than 4 centuries, right? It really goes back to every ancient culture. But since I'm a big sucker for Newton, I put that date. But it's really, humanity, we've gotten to this point where we have such precise equations. Well, there's trouble in paradise, to echo Thomas's words. There are 2. Why not 1? Seems like a natural thing to do. Why not just 1 set of equations? I mean, if you want to have a unified framework for everything, why not just have 1 set of equations instead of 2? Well, that's exactly what this guy thought. And he's a very, very smart guy. So Einstein, together with many of his contemporaries, tried to unify the left side with the right side. And it's quite amazing because at that point, he didn't even know the Higgs particle existed, right? He was just really trying to put as much as he could. Einstein died in 1955, trying to put these 2 together. Here's a shot of his office the day he died. Apparently, on his deathbed, his last notes were trying to unify these 2 equations. Don't mean to get sentimental here. I'm not trying to get morbid, but I've told you a lot about death of mathematicians here. But it shows, in some sense, it shows our devotion to the subject, right? On your deathbed, you want to be working on this. And Einstein couldn't do it. And this problem is a technical problem called the unrenormalizability of gravity. Okay, so this is a technical problem. So I'm going to bore you for 23 seconds of this technical problem. So what I wrote down in those things are called Lagrangians in mathematical physics. Lagrangians are additive functions. So you can just add Einstein did this thing, he literally added the 2. One for gravity, one for the particles. And then what you do in mathematical physics, you run through the standard canonical quantization procedure, and you do run this procedure, and boom, you get an infinite number of uncancelable infinities. That sounds bad even for us, right? And Einstein ran into this problem, and I was like, oops. And if Einstein says oops, it means it's really hard. So Einstein was literally working on this problem. I don't have a high enough resolution. I really want to check whether those equations are his attempts in trying to unify. Historically, I need this to be enhanced just to check this. But on his deathbed, you could see his notes was trying to do this. But Einstein's a smart guy, but he knew what he was after. He knew that had he succeeded, he would have gotten this. And that is why this is the title of that great movie. I think it's a very touching movie about Hawking. And Hawking was, of course, following the footsteps of Einstein, literally trying to unify these 2 sets, the theory of quantum gravity. One of Hawking's greatest contributions was to come up with the semi-classical approximation of black holes. So that's where you almost make these 2 worlds talk to each other. Well, there are many reasons, almost philosophical, why you get this incompatibility. Because one is at a very large scale, the scale of galaxies, and the other is at a very small scale, right? And you're trying to match 2 very, very large disparate scales, right? That's one reason. Another reason is, Einstein's greatest feat was to show that gravity is not a force. It is the curvature of space and time. So if you wanted to unify these 2 Lagrangians, you're not really faced with the problem of quantizing a force, which we're used to doing, like the great, forefathers of quantum field theory. But you're trying to quantize the very structure of space and time. And that's hard. But then you say, well, is it even relevant? Why should these two disparate problems ever talk to each other? But they do. We know they do. For example, at the moment of creation, at the Big Bang, there is no microscopic or macroscopic. There is only that point. Near that point in the space-time continuum, we knew there must be some kind of a unified framework. Right? And, in addition to that, at the center of black holes, they also talk to each other. And the famous singularity theorems that Penrose, which Thomas and I had the pleasure of interviewing just last month, got the Nobel Prize for. But we know it has to happen, but we run into this technical problem. And so Einstein actually coined this word, the theory of everything, TOE. If you read it, it's a horrible acronym because it says big toe. But hey, it is what it is. And very touching movie about this quest, a very precise mathematical problem of the theory of everything. Just to make you very excited, here at the Royal Institution, I think I'm going to open the door, but if you just walk out down the corridor, was one of the first receptions in honor of this movie. So Eddie Redmayne played Hawking, of course, and Hawking himself came. And that's not Marilyn. Hawking has not invented time travel. This is a very good Marilyn impersonator. I unfortunately, I don't think this is before our time, otherwise we would have definitely crashed this party. It would have been awesome. That's so cool. But back to our problem. This is the theory of everything. This is a very precise problem. The quantization, the gravity, the unification of these two Lagrangians. Well, you could just give up, right? And I declare, there are just two sets of equations which govern all of reality, right? But I've already given you several reasons why we shouldn't give up. But from an aesthetical point of view, and aesthetic is something I will repeatedly emphasize, I love this quote of Einstein. The most incomprehensible thing about the universe is that it is comprehensible. This is why we do basic science. It's almost religious. It's a cosmic religious feeling because we can understand it. I don't know why. This is one of the great sayings of Einstein. Fine. The philosophers Popper and Kuhn tell us, in the history of science, whenever you run into a problem, you go through what's known as a paradigm shift. I'm not a philosopher, but it just sounds like a seriously impressive word to use. Paradigm shift. So a typical example of a paradigm shift was when Newton's gravitational equations I mentioned earlier could no longer explain the precession of Mercury around the sun. Einstein said, wait a minute, it doesn't work not because you're not doing some calculation right, but because your theory is should be fundamentally readjusted. Gravity is not a force, it is the curvature of space-time. Redo the calculation, now it works. Right? That's a typical example of a paradigm shift. We're faced today, in the 21st century, with another need for a paradigm shift. Right? And here's a paradigm shift. This is thought of by a group of theoretical physicists and mathematicians in the 60s and 70s. And they went to something pretty radical. So these are, I can't even start naming it. John Schwartz, Michael Green, Edward Witten, Veneziano, Verasoro, and the whole list of great minds. And they were like, we've been misled. We've been misled since the time of Democritus. Democritus is the Greek philosopher who came up with the word atom, atomos, the indivisible. Okay, so that was, ancient philosophy. But the idea of the point particle was something that was always used. Newton famously formulated his entire Principia in terms of dynamics of point particles. Even quantum mechanics, right, is a theory of waves of point particles. So these guys, they said, well, let's do something different. Let's do something radical. Let's assume that the fundamental constituents of reality are not point-like. but they're rather smeared out to some extent. Well, if you have a point particle, you smear it out, what do you get? You get a loop or a string. And this was the birth of superstring theory. Okay, let me just address this let me just parse it for a bit. Well, it seems pretty arbitrary, right? First of all, how big is the string? To what extent must you smear out the fundamental constituents of nature? Well, the universe gives us a hint. This wonderful equation here. Let's take the fundamental constituents, the fundamental constants of nature. There aren't that many, right? Most constants, fundamental constants, are derived from these, combinations of these. Well, there's h bar, the Planck constant, which governs quantum mechanics. Okay, that's got to be in there because we're trying to quantize something. There is G, that ancient and the first of the great constants, the gravitational universal constant of Newton. These have numbers. Because I'm a theorist, I don't really remember these numbers. I think G is like 6.7 times 10 to the minus 11. I mean, they have units. And Planck h bar is like 1.3 times 10 to the minus 34. You can convert okay. Google it later. C, I know, is the speed of light, 2.99 times 10 to the 8th meters per second. These constants are the constants of nature. Any civilization, alien, Martian, us, when confronted with this fundamental problem, will have realized that these are the fundamental constants of nature. Right? There is a unique combination. This one, the square root of the product of the Planck constant, 2g Newton divided by the cube of the speed of light, which is in the units of length. This length is called the Planck length. This is a universal length scale to the universe. In human units, it's 10 to the minus 35 meters. I will address that in a minute. But the universe is speaking and crying out to us. The universe is giving us a hint. At 10 to the minus 35 meters in human units, something has to happen. Something has to happen to the very structure of space and time. If you were to have a theory of everything, you must have this dimensionful constant in your theory somewhere. It's only natural to declare that these superstrings are about this length scale. Natural assumption. Nothing there. Just to give you an idea how small this is, okay? To my knowledge, CERN, the best experiment on Earth in terms of zooming things in, can detect 10 to the minus 18 meters. This is about 17 to 18 meters of orders of magnitude smaller than anything we can detect with our current technology. Right, you remember that 19 decimal places is the width of the solar system to within a hair. It's that order of magnitude smaller than what CERN can detect right now. So we really need to go back to the origin of the universe to see the cosmological scales to be able to detect something like this. Okay, this is a saving grace for mathematicians, by the way. I'm going to go there in a minute. So, fine. Very simple paradigm shift. You assume that the constituents of nature are not point-like, as we've been deceived into thinking all these centuries, but rather they're smeared out into little strings. And so here's a diagrams that depict the joining up and interaction of strings and so on. Fine. You run through the math. Archimedes is not involved in this. But had Archimedes been alive today, he would say the very same thing. Eureka! We do get a consistent theory of gravity, the theory of everything. So you may hear reports otherwise, but string theory is a consistent theory of everything that unifies quantum mechanics with gravity. Here it is, in its full glory, a string action whose perturbation series, that is the Ricci curvature, for general relativity. This is the gauge bosons in the standard model. They come out for free in this beautiful Fourier expansion of this Lagrangian. So why am I here? This is the end of science, right? In some sense it is. Well, I should be out on the beach drinking pina coladas because this is it, we're done, we're finished. We have finished not only the dream of Newton, we have finished the dream of Archimedes and every philosophy that ever was. I should be celebrated. But I'm here. I'm not on the beach. I mean, I don't mind being on the beach. But everything comes with a caveat. And the caveat here is that it only works in 10 dimensions. It's a very strange caveat. I like it, I love it. Because this is the first time a physical theory has made a prediction about this dimension of space-time itself. No previous theory has ever even tried to do this. It's pretty cool to me. Right? It's okay. If you're freaking out, don't worry. CERN is working on it. I know some colleagues of mine at CERN are actually working on it. So Higgs is done. Standard model finished. With Higgs boson done. Last God particle finished. Two of the key experiments now at CERN, one is to discover supersymmetry, and one is to actually detect extra dimensions. I have no idea what they do. I visit CERN from time to time. They keep me very far away from the machines. It's like I jinx it or something. I just like admire. Ooh, look at those blinking lights. It's amazing. The theory group at CERN has its own building very far from the accelerator, in case we go in there and press the wrong button. I'm very tempted though, but they're actually working on it. It's a beautiful set of experiments working on this. So, but back to theory, right? We have a unified theory of everything, a theory of quantum gravity in 10 dimensions by these strings. Oh, by the way, I've just picked my mug. By the way, you know those equations? You can buy mugs that have this. It's nice. So Victoria's very kindly giving me like this chalk things. You can just buy this blackboard chalk cup. This is the universe. That's it. All of it, right? All of it, too. One day, I hope there'll be... actually, you know what? You should buy one of these mugs, and I will write out the string Lagrangian, and then that's it. It also fits on the mug. But that's the whole point of theory of everything. But I'm drinking from my LIMS mug instead because it's cool. So back to theory, right? Back to theory. We have a theory of everything in 10 dimensions. We don't live in 10 dimensions, but it's pretty darn obvious we don't live in 10 dimensions. We live in 4 dimensions. There's 3 of space and 1 of time, right? That's okay, can't argue with that. Nor can you argue with this equation. You know, you may be a string theorist or not, but nobody can deny the fact that 10 is equal to 4 plus 6. So what's the point of this equation? Is that there are 6 missing dimensions of space. Well, doesn't bother us. Because imagine this ant. This ant is crawling on a twig. To the ant, the universe is 1 plus 1, or 2 dimensions, right? There's 1 of space and 1 of time. But we know the ant doesn't. The ant lives in 3 plus 1 dimensions. The ant hasn't been aware of this tiny cross-section of the twig. It just hasn't been clever enough or cared enough to discover the cross-section. And that analogy is perfect for us. We are ants living in 10 dimensions, but we think we only live in 3 plus 1 or 4 dimensions because there's these 6 tiny dimensions that we haven't detected. How tiny? Well, Planck length scale. And that's why we haven't seen it yet. And that's exactly what CERN is doing. One of the experiments in CERN is doing is to try to detect those missing dimensions through some ingenious... We need an experimentalist as great as Faraday to be able to crack that. Now it's an experimental problem. The theory is there. I give it to you. But we need a Faraday. We've got the Maxwells, but we need a Faraday. And I'll get back to that in a minute. So that's fine. Theoretically, this is not a challenge, right? The ant and the cross-section. We're just ants, we haven't discovered the cross-section. And our cross-section happens to be 6 dimensions. Okay, let's jazz it up a little bit. The next indisputable equation is that 6 is equal to 2 times 3. Right? In the seminal paper of Candelas, Horowitz, Strominger, and Witten, they realized that a great solution to the 6 missing dimensions is a class of spaces, these curled up shapes, called complex manifolds. In fact, complex Kähler manifolds. In fact, complex Kähler manifolds of flat Ricci curvature. I just want to throw these words at you because they're so cool and they sound so fancy. You can impress people at like cocktails, right? Let me just go through a tutorial. Bear with me. A tutorial on complex geometry in 5 minutes, maybe 3. Depends on whether to fall asleep. So we all know what the real plane is. Right? This is the Cartesian plane that we were taught when we were 3. It's this 2-dimensional plane. And one of the greatest leaps in mathematics is to realize that this real dimensional 2 plane has what's known as complex structure. You can create this new number called a complex number whose real part is this and whose imaginary part is this. But it has complex structure in the sense that you can multiply. So it forms what's mathematically called a field. Well, fine. Imagine folding up 6 real dimensions pairwise into 3 complex dimensions. And what you get there is a complex manifold or complex space. And what these guys realized was that physical constraints put on this unified theory in 10 dimensions forces your extra dimension to be of this type. It's kind of cool. I want to emphasize, now we've gone beyond this original solution, and we can do more sophisticated geometries, but this still remains one of the favorite solutions of this reduction. So why did I mention this? Well, it's because I want to emphasize that this is another great illustration of that great fact that the language of physics is mathematics, right? We've started with this physical problem of trying to unify Lagrangians, blah, 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 and we're led to a field of complex algebraic geometry, which is what I do. And this is a wonderful quote from Galileo, that, if you want to ever do anything serious in physics, mathematics is the language with which God has written the universe. Here's a shameless self-advertisement. Recently, I was very honored to have co-edited this book with C.N.Yang, the Nobel laureate that I mentioned earlier. He's turning 100 next year. He edited this book with me when he's 95, or just before COVID. And we had contributions from Penrose and all these people. Don't listen to me, Babylon. These guys wrote what they thought in this book about what the current progress of topology and geometry is and what the language is for physics. By this book, I get royalties. Right. Moving on to serious stuff. Now I'm going to give you a tutorial of complex geometry, as I promised, right? I'm going to start with a tutorial in complex geometry in dimension 1. And this is a story that goes back to Euler, Gauss, and Riemann. There's a classical theorem of Gauss. So complex dimension 1 means real dimension 2. Real dimension 2 means they're surfaces, right? Shapes of surfaces. And Euler had this beautiful theorem. It's a mouthful, that all compact, smooth, orientable surfaces with no boundary can be topologically classified by a single integer, which we call Euler number. Well, he didn't call it Euler number, we call it Euler number. It's this number chi. And this number is intimately related to the number of holes. The surface of a sphere has no holes. The surface of a donut has one hole. And everything that is topologically equivalent to the donut has one hole. For example, the mug. You can continuously deform this mug to the donut. Can't eat it, but... and higher pretzels of every country. German pretzels, Chinese pretzels, they're higher ones. So Gauss comes along, and he says there's an intimate relation between this integer, the Euler number, and the curvature of your surface, in what Gauss called his Theorema egregium, his great theorem. This is Gauss's great theorem, so it must be pretty damn good, right? What he did was to show that if you integrate the curvature over these surfaces, divided by 4 pi, you get an integer that's exactly this Euler number. It's beautiful. And I won't bore you with the details. This donut shape is the only one that's what's known as Ricci flat. It has 0 curvature. This is positive curvature, what's called spherical geometry. This one is Ricci flat, known as, well, I won't give you the name yet. This is hyperbolic geometry of negative curvature. 150 years of geometry. Beautiful. Right? But this is just a tutorial of topology and algebraic geometry in complex dimension 1. We need to go to complex dimension 3. As you go up higher in dimension, life gets harder. It's very, very difficult to study high-dimensional manifolds. The Poincaré conjecture famously took 150 years to settle, and that's only real dimension 3. Right? So it's a very difficult problem. There's so many ways to put shapes in higher dimension. So here's an analog of that beautiful picture in complex dimension 1. You can't do it in general, but for a very special class of manifolds known as complex scalar manifolds, you have an analog of that beautiful story of Euler, Gauss, and Riemann. I won't bore you by reading out this theorem, but this is Clapia's conjecture in 1954, 57. It just looks so beautiful, doesn't it? Like so aesthetically beautiful. It took almost 30 years before Xintong Yao proved this conjecture, for which he was immediately awarded the Fields Medal, the highest honor in mathematics. So why? Because it's such a central problem, right? Because these guys are trying to generalize the great theorems of Euler, Gauss, and Riemann. So he was see, that's why he's so happy. He got the Fields Medal, right? I don't know, maybe he looks less happy. I don't know, but they're both alive. So Yao is one of my very close collaborators as a very insightful geometer. Anyhow, so at least for these manifolds, there is a generalization of that beautiful theorem. Fine, okay, that's it. That was the end of my tutorial for complex topology. I see people like, gosh, I'm done. All right, fine. But it was fun, wasn't it? Beautiful equations, just so beautiful typeset and everything. What are Clapia geometries? I told you in complex dimension 1, there's only the surface of the donut, right? In complex dimension 2, using these results of Yao and Calabi, there are 2 of them. There's the 4-dimensional donut, and then there's this special thing called the K3. In complex dimension 3, the one we're after, because 6 is 2 times 3, we have absolutely no idea. This is a very strange sequence in mathematics. It goes as 1, 2, no idea. You would say 3, right? But it's not. No, not every sequence that goes as 1 and 2 ends in 3. This one, so far, we have discovered over 10 billion topological types. It is what it is. I'm not like doing, it's just what mathematics forces us to do. C'est la vie. But at least what's cool is that, my 4-year-old asked me what I do all day. I said, well, I do the higher dimensional generalization of the donut. He's totally his hero now because, like donuts in 6 dimensions. That's so cool, right? How long would you take to eat that? Right? But I want to emphasize something else. So I've given you 2 trains of thought. One is the tradition of Euler, Gauss, and Riemann from pure geometry. And then there's that paper of Candelas, Horowitz, Strominger, and Witten from pure physics. They converged. They didn't know each other at all. This was just, when that paper came out in 1985, it just so happens that physicists for the first time saw these things. What are these things? They're some kind of Ricci flat you may understand from Einstein's vacuum equations, but what are these strange conditions of complex scalar? And then it just so happens in 1986, Strominger and Yao were in adjacent offices at the Institute of Advanced Study in Princeton. And Strominger, the physicist, went to Yao and says, what are these complex Strominger? And then Yao says, oh, I think I may know a few things about them. I just got the Fields Medal for it. And that began this wonderful dialogue between mathematics and physics. And when that happens in the history of science, you know you're onto something. Right? This is not accident. So Candelas was my mentor when I was a junior research fellow in Oxford, and he tells me these wonderful stories about this accidental convergence, which led to so many. That was 85, right? Since then, so much more have come out. Another shameless self-advertisement. If you want to read more about the history and the mathematics of Clapia manifolds, you can buy this book. I get royalties. But this is a technical book, and it's much less interesting than the one before, which actually has the thoughts of great minds. This is just me blabbering. But at least if you're a graduate student, you want to read about the Clapia geometries, this is the book. But if you really want to know what a Clapia geometry is, in January, a team of Chinese game developers created this game called Clapia. I mean, this is Clapia in Chinese, Clapia. I'm not a gamer, so I have no idea what this is. But there's a QR code, you can download it, and then I think you could, you blow things up with beautiful people. I have no idea, I'm not a gamer. But I think it involves blowing like Clapia manifolds. I don't know, it looks cool. Just scan it and it's cool. I'll scan it at your leisure, and you can play this game. So let me summarize. We have this indisputable equation of string theory, that in 10 dimensions we have the theory of everything, a theory of everything. There are other contenders, of course, like loop quantum gravity, foam, and other stuff. Of course, they all involve the Planck length. But if I were to put my money on it, I'm going to do string theory, and I can explain why. Minus the 6 dimensions, this real dimensions or 6 dimensions of the complex manifold, which is Clapia that I told about. You're going to go home and tell everybody about Clapia manifolds. They're awesome. You can impress people at cocktail parties. Hey, here's a Clapia manifold. It generalizes the Euler-Gauss-Riemann theorem. And people are like, oh, this is so cool. Right? Highly encouraged. Great way to, I don't know, pick up dates, I don't know. You get 4-dimensional universes that can be created from this, right? So this is my 7-year-old asked me what I do for a living. I said, well, create universes. And I'm like totally like a superhero to her now, right? But the point is, you reduce on these geometries, and the geometries of this, in this class of manifolds, Clapia manifolds, dictate the properties of universes. And we want to find the one that's like ours. But it's wonderful, because this falls into that program known as the geometrization program of physics. Throughout history, since the time of Newton, increasingly we have this sequence of efforts of making our world into pure geometry, into pure mathematics. And here, a wonderful quote from Johannes Kepler again, back to Kepler. Kepler, in a mystical way, said, where there is matter, there is geometry. Like declaration. Ubi materia, ibi geometria. Well, string theory is the answer to that question, the ultimate answer to this question, because it is a complete geometrization understanding of all of the particle interactions of the structure of space-time. So is general relativity, and so is the gauge theory of quantum field theory. They're all a geometrical or purely mathematical description. But here comes the problem, right? This is a theoretical problem. I already told you about the experimental problem of there's no experimental data. But here is a theoretical challenge. We already saw 10 to the 10th, and that's just the corner of possible geometries. There are just simply too many ways to reduce this theory of everything onto our four-dimensional universe, or any four-dimensional universe. Some of them, okay, fine, will give complete crap. You could produce like 17 generations of electrons or 25 different Higgs particles, which we don't see. Fine, we rule them out. But how do you rule something out from something that is as big as this? This is a famously quoted result that there's this proliferation of possible geometries, and you can't even sift through this in any efficient way. So this is called the degeneracy problem, and this is the biggest theoretical challenge to the theory of everything, for string theory. For me, this is much, much more interesting, because string theory has traded a hard problem, the quantization of gravity, by a problem in geometry and in pure mathematics. And this problem has generated so much dialogue between theoretical physicists, pure mathematicians, computer scientists, and now data scientists. I'm going to mention in the next slide, well, some of the last slides. It's much more interesting. I'm not a string theorist in the traditional sense. I don't write down string Lagrangians and try to quantize them and beat myself until I cry. I take the much funner problem. I take string theory as my input, and I just explore the geometry and see like, wow, this is so cool. It's a very nice way to explore different types of geometries. But confronted with this kind of numbers, one of the things that I've been thinking about recently, well, with this amount of big data, everybody's doing this these days, right? Machine learning, AI research. So one of the things I was doing in this paper was to say, well, you got this enormous amount of statistics of pure mathematical data. Machine learn them, so whether that's possible. Surprisingly, this is good. I mean, I can tell you, I can go on and on about this, but I won't bore you with this. So it's leading me to where like this machine learning idea is really a very fruitful approach to this dialogue between pure mathematics and fundamental physics. But let's get back to scientific data. So what I talked about there was pure, noiseless, structured mathematical data. Now let me just go back to the last part of my talk, which is, what do you do with a theory that has no experimental data? Yes, play all you want, but what do you do when there's no experimental verification of any way, of any form? CERN is really working on it. Some of my colleagues are really trying to find stringy signatures, even in cosmological signatures from the early universe. Can only hope, right? But rest assured, this is the story of mathematical physics all the time, right? I said in the very beginning that there is a dance of discovery between data, pure mathematics, fundamental physics. Sometimes they're ahead, sometimes the other one is ahead, right? Countless examples have existed in the history of mathematical physics, in the discovery, in this quest for the theory of everything, in which the theory far predated the experiment. For example, the Higgs. For example, Dirac's equation of the prediction of the positron, etc., etc. Now, of course, Dirac is a fanatic in this sense. He famously said that it's more important to have beauty in your equation than to fit experiment. Okay, I'm not that fanatic, but hey, who am I? But he's Dirac. If Dirac says something like this, we should take it seriously. Just to give you, so here's a monument of, oh, by the way, this is a really profitable thing to do, mathematical physics. Because if you die, you do something great, you get tombs that this impressive. So this is Newton's tomb in Westminster. I think that direction. I mean, it's all in London, right? You guys should be so proud that you're Londoners. And at his feet are buried Hawking and Dirac in Westminster Abbey. I encourage everyone to go see it. It's a truly, I go in there and pay my homage or whatever I can. There's it's like I'm not worthy, and try to get whatever inspiration I can get. So let me just conclude with a story that happened in this room, maybe, possibly, or certainly in this building. The story of Faraday and Maxwell. To just give you a home in on this idea, when there is no experimental data, you should not be afraid. You should never be afraid. You should go for mathematical beauty. Always go for that, because you always lead you to the right path. So here's another example. So Faraday, of course, was the director of the Royal Institution here. His friend Maxwell comes down from Scotland. He was the greatest experimentalist of his age. He's one of the greatest theorists of his age. Maxwell learned from Faraday these set of equations, which we now call vacuum Maxwell equations. I won't bore you with the details, but here is the electromagnetic induction term that Faraday famously discovered, that moving magnetic field induces electric field. So that's how to read that equation. Doesn't matter. Now I challenge a member of those several. If you don't have a degree in the sciences, if you have a degree in classics or music, can you just tell me what is wrong with this set of equations? Does something look wrong to you? And if you have a degree in math, don't say. Anybody? Good, thank you. Victoria has a degree in business. Good, excellent. Excellent, thank you. So Victoria pointed out that this looks kind of not symmetric. And that's exactly what Maxwell thought. This just doesn't look right. It would look so much more elegant if the set of equations looked like this. And now it's more balanced. That's it, that's all he said. And that term, encircled, is called the Faraday Maxwell term. It is because of this term we can now solve these partial differential equations and get a wave equation and get light, and the rest is all history. Why did Faraday add this term? Because there was experimental data? No, he added because it was just more mathematically elegant. We had to wait 10 years after Faraday's death for Helmholtz to verify this term. And it's true. Now it's been verified to however number of digits of precision. This is very interesting. In 1959, the Nobel laureate Eugene Wigner wrote this essay on the unreasonable effectiveness of mathematics and natural sciences. So that's an essay in which he writes, why is it that nature's language is written in mathematics? Curious, it works. What's less known is in 2010, the Fields medalist Atiyah and Digraph, who is the director of the IIS at Princeton, and Hitchen, who is the Savilian chair of geometry at Oxford, they wrote this response essay to Wigner, in which they famously wrote, to our community, famously, this is a much more famous thing, they wanted to invert this comment of Wigner and say that, there's an unreasonable effectiveness of physics in mathematics. And they were referring to these new ideas in string theory. So Hitchen works on this thing called Higgs bundles, and very much a part of this community of mathematical physicists at the intersection of mathematics and physics working in string theory. And it's very interesting because every mathematician, pure mathematician I've ever talked to, everyone without exception, and asked them, do you think string theory is the right way to go? Yes, 100%. Because I have never seen a theory like this that gives us so much new math to do. If you are a physicist, 50-50, you're like, meh. The other 50 says, and there's some proponent says, no, it's just wrong. But I think if you sum them all up in the community, I think the ones that said it's right, it's at the majority. Why? Because it generates new mathematics. And that's, this beauty is a very strange criterion. It is not subjective. Mathematical beauty is not subjective. It has to be concise, it has to be self-consistent, and it has to link and generate new ideas in mathematics. When your theory passes through these tests, chances are they're correct. As time again, history has shown us. The Dirac equation, the Faraday Maxwell term, etc., etc. That is why I do, stringy-inspired mathematics, as many of my colleagues do. In fact, if you plot so these are the groundbreaking papers in physics. Einstein's general relativity, Dirac's quantum electrodynamics, C.N.Yang and Mill's theory of gauge theory. And these are the mathematical ideas which inspired them. General relativity was inspired by Riemann geometry. Dirac equation was inspired by the Clifford algebra. C.N.Yang's work was inspired by Cartan and Seiferd's work on topology. It's pretty clear what's happening. The distance between the two is convergent. We're right around about this point when the physicist Witten got the Fields Medal for the first time a physicist would ever gotten the Fields Medal, for trying to prove a major result in topology using ideas of supersymmetry, a physics idea. At the same time, Borcherds, another Fields medalist, used the idea of vertex operator algebras from conformal field theory and string theory to prove one of the most profound theorems in representation theory of finite groups, known as the moonshine conjectures. We're convergent. We're at this point where new mathematics and new physics are being generated, and that happens in string theory, and it doesn't happen in any other field of contention to this theory of everything. This is why we work on it. It's fun. And the measurement, of course, is beauty. So let me conclude with this great quote poem of Keats that, beauty is truth, and truth, beauty. That is all you know on earth, and all you need to know. And that equivalence of truth and beauty in mathematics is the very logo of the London Institute. Thank you.